am Minjae JEON, and today I'm going to introduce the basic math used in electromagnetism. It might be easy at the same time hard. To exactly express the nature's law, it must use derivatives and integrals. This lecture PowerPoint mainly includes del operators that are widely used and also the basics. I will first start with the del operator I introduced in the first slide. As in the PowerPoint, del operators are declared as two similar equations. Before understanding the declaration, the symbols must be known. The three dashes instead of the equal is a symbol that is used when someone should declare something in math. The arrow above the nebula is called the vector sign, which has a size and direction. And the symbol used in fraction is called round. Round is used as a partial differentiate when there are more than two variables to derivative. The hat above I, j, k is called hat, which is a unit vector that has size of 1. That means unit vectors has only directions. The first declaration is used in third dimension space, which is common. And the second declaration is a generalized form of the del operator that can be used in higher dimension space. And next slide. Now we will see the application of del operators. The first application is gradient. Gradient is a slope of a scalar function. It cannot be used in a vector function. Gradient is used before the scalar function to calculate the slope of the function. Gradient can also be generalized until the nth dimension, as shown in the before slide. In the picture, the contrast of the color shows the size of the scalar space, and the blue arrows shows the gradient, also called a slope. As gradient make a vector field that is also used in electromagnetism. For example, it can be electric field or it can be magnetic field. Or in like fifth mechanics, it can be gravitational field. The second application of del operators is divergence of a function. A divergence is declared as inner product of del operator and a vector function. Divergence is important because it is used to find the direction of a vector field. If the direction of the field is known, we can find the higher density part from the space and also as lower. The equation is the equation in the bottom is the proof of how the divergence of a function can be expressed as algebra. As you see in the equation, there is no unit vector that exists in the progress. This means that divergence of a function is a scalar product. Also, the picture shows how divergence works in vector field. If the scalar amount is negative, it converges, and if it's positive, it diverges. However, if it is zero, neither happens. As introduced in the slide before, these are the two different definitions of inner product. As in algebraic definition, A and B are expressed as a row matrix. A is a matrix which element is A1 to AN. Similarly, B is a matrix which element is B1 to Bn. So finally, the inner product is defined as the sum of the multiple of each elements in the matrix. As geometric definition, it uses two vectors A and B in the coordinate plane. The result of the inner product shown in the slide is the multiple of A and b and cosine theta, where theta is a contained angle between vector a and b. The third application is the curl of a function. The curl of a function is expressed with outer product of the del operator and the function. As shown in the equation, curl of a function is a vector amount, not a scalar amount. Because curl is a form to calculate the rotation of the function, it is also important while defining a function's movement. We can determine the rotation by the scalar amount in front of the unit vector. If it is negative, it rotates counterclockwise. And if it's positive, it rotates clockwise. And if it is 0, there is no rotation in the function. This slide is the proof of calculating the curl of the function. It uses matrix as similar in inner product. It uses matrix to calculate the amount. So the bars in the end of the 3 times 3 matrix is used while getting determinant of the matrix. The equation has the same form of calculating determinant of a matrix. The general meaning of curl is a scale of the rotation in the vector field. The picture shows that meaning. By learning divergence and curl in this lecture of a function, we can precisely describe the motion of the function in the field, because divergence shows the way the function is directing and curl shows the rotation. I will explain the outer product or a cross product used in curl of a function. It is defined as two ways, algebraic and geometric. First, in algebraic, it uses the way calculating the determinant of the matrix as explained in the before slide. The geometric definition is similar to the definition used in inner product. However, outer product uses sine theta instead of cosine theta. From now, I will introduce the second derivatives using del operators. The first one is divergence of gradient. This is very important in physics because it makes a Laplace operator, also called as Laplacian. By using the definition of divergence and gradient, we can get the final equation. It is a square of del operator. This product is scalar since it used inner product. The square of del operator is called a Laplacian, and this is one of most important symbol that is used in physics. More concepts about the Laplacian will be explained at the next page. A Laplacian is expressed as the equation in the page. This Laplacian is a second derivative of a function. As expressed in the graph, the first derivative makes a peak at the turning point of the function. And finally, at the second derivative, the peak becomes a 0 in the graph, also a turning point again. This means it can use Laplacian to divide the boundary of different color or properties. If it is used in physics, it is an important factor to find the boundary condition of a field or etc. The picture of Einstein above is the example of usage of Laplacian filter to make the boundary of a drawing. As a drawing is a black and white picture, the contrast between the color makes a boundary in the drawing, and by using this filter, we can show all the boundaries of the drawing. This slide shows the example that uses divergence of gradient to express a relation between electric field and the potential to a clear form of potential calculation. As mentioned in the slide, the electric field is same as minus gradient of potential and divergence of electric field is constant as written. So if we combine two equations, it makes conclusion as Laplacian of potential is minus rho over epsilon zero, where rho is density of charge and epsilon zero is permittivity of vacuum. The result is important in physics because an equation that is constant or zero is widely used to eliminate some variables in equation. Also, if equation of potential is used commonly when someone is calculating the potential in the space but has no other information such as electric field. In this slide, I will explain curl of gradient, which is similar to divergence of gradient. Curl of gradient is also important as divergence of gradient, but not as much as divergence of gradient. Because the final result is zero, it has many meanings that is implicit. The calculation of the equation is similar to curl of a function. As physics like a result zero or a constant because it can be eliminated with calculation, curl of the gradient is one of the most used equation in physics. Because the curl of a function is a vector, it is complicated and has to think the relation between different direction amounts and numbers. However, if the result is zero, it means all size is zero by all direction. Finally, I will explain direct delta function. Direct delta function is a function's graph is like in the picture. It is defined as if it is not zero, then the function is zero. And if the x is zero, the function is infinite. The equation integral minus infinite to infinite delta x dx, this is the area of direct delta function that is defined. And the surprising thing here is that it is constant as 1 always. As shown in the slide, two direct delta functions are used in different dimensions, 1 and 3. But the results are the same as 1. So this also means direct delta function can be also expanded to nth dimension, like the definition of del operator. This is all important in advanced physics. These are used in Fourier transform or integral transform while they want to choose only one point of the function. Because of the unique characteristic of direct delta function, it is used importantly in finding point size. Today I explained about the basics math used in electromagnetism, and thank you for listening to my presentation.